We go with video 6G, covering questions 6 to 8. There is a lot of content here. This video could be quite long. I will at times try to go quite quickly to avoid this, but for something like question 6, it's not really possible. All right, question 6. So we have Bandicoot Island, and it has a maximum capacity, maximum population of 20,000 rabbits. 50 years ago, so t equals 0, 100 rabbits were released. So t equals 0, p equals 100. And now there are 10,000 rabbits, so that was 50 years ago. So now t equals 50, population 10,000. So it's grown 100-fold in 50 years, but it's not going to grow 100-fold in the next 50 years because we're already halfway to the maximum population. Question A. Using this differential equation, which is a logistic equation, model the rabbit population, find the number of rabbits there will be in another 50 years or 75 years. Now, there's an important note here. If we just think ahead, we've got dp dt equals kp m minus p. That's the max, so that's 20,000. P is the population, of course, that's a variable. K is a constant. Right, now that's a growth rate, but if you compared it to dp dt equals kp, that's exponential growth, and dp dt equals kp maximum minus p, they're reasonably similar, and they can produce similar looking graphs until you get to the slowdown bit. But the value of k will typically be very different. The k in this one will typically be much, much smaller than this for a similar looking curve. I just want to put that out there. Okay. In this note, we'll need to show the following algebraic result. Okay, so if you look at the differential equation, then we're going to need to take reciprocals, aren't we? So that we can integrate with respect to p. We'll see that very soon, but I think you can imagine that. When we do that, we're going to have something that we would have trouble integrating. So this note allows us to get through that. So put simply, we can't integrate that, but we can integrate that. All right, and they're equal to each other. So it's part of the question that we have to show this. And in an exam, it would typically be a 1-mark part 1 question to show that, because you can't get anywhere without it. All right, let's push on. So I'll do this bit first. So how do we show that? Well, the right-hand side is 1 on m, and now we'll have a combined denominator. We can cross multiply, so we've got m minus p plus p. All right, we get some cancelling there, so and that's 1 on, no, sorry, that's m remains there, p on p m minus p, and now we get the that cancelling. I don't like doing cancelling in my working, but it's important when I'm demonstrating this. It's important to get that right too. And that is the left-hand side. Okay, so a question like this does not pose any difficulty. It's just part and parcel of working with a logistic equation. Right, so we're taking that for granted now. All right, A. So we have dp dt equals that. So taking reciprocal, I'll put the 1 on k separate. Okay, and so if we integrate, and now we use this to sort that out, right? And so t is 1 on k times the integral of, well, I've got 1 on m. I should have taken that out, but I'll, I suppose it's best to okay, and now I'd like there's a negative p there, so I'd like that to be a -1 so that we can take the logarithm. Sorry, take the primitive and get a logarithm. Remember, m is a constant. M, I should note here actually, m equals 20,000, but there's no way I'm going to go through all this working writing 20,000 on every line. K is not known at this point. So 1 on P, so the m's been taken out the front, the 1 on m, 1 on P minus -1 on m minus P. Okay, finally we can actually take the integral. So 1 on km, integral of 1 on P with respect to P is log of absolute value of P, and then minus log of absolute value m minus P. Okay, and we've got plus C, of course. So I've moved the C over and used logarithm laws there. And okay. Notice that the only variable over here is t, everything else is a constant. And now exponentiate both sides, so absolute value P over m minus P equals e to the kmt times e to the negative kmc. And because this is all constant, we want to replace that with an a. Oops, not negative kmt. Right, so a is greater than 0 because it's e to the something. And now to get rid of the absolute value signs, this is nothing unusual now. Right, and so that we've loosened the restriction on a. So a can be greater than 0 or a can be less than 0. What about a equals 0? That's certainly what I've indicated here, but that would mean that we've got a 0 solution here. So p equals 0 is a solution here. I'm just going to make a note here in a different color. P equals 0 is a solution to dp dt kp m minus p. Right? See, that would zero out the whole thing, the whole right hand side. And And so that means that A can be 0. I feel it's a bit premature to talk about that at the moment, but anyway, we'll move on. Okay, need to create some more room for myself. Carrying on. So P equals, if we're going to multiply by m minus P, then I've got A m e to the k mt minus A p e to the k mt. So I've got, basically in this line, I've got P in two places. I want just P by itself. So multiply by m minus P, fully expanded. And now to get P by itself, then this term has to take a journey to the left. And I can factorise. So P 1 plus A e to the k mt equals A m e to the k mt. Does all this seem like a lot of work? It is. And now P equals A m e to the k mt over 1 plus A e to the k mt. Notice that this and this are very similar. The only difference is that, right? And this is more complicated than it needs to be. We can simplify it a bit by doing something a little bit special. We're going to divide top and bottom by what they've got in common, and that is A e to the k mt. That gives us P equals m over, now the 1 divided by the A e to the k mt is A to the negative 1 e to the negative k mt, and then we've got plus 1. And so now we'll let capital B equal A to the negative 1 to get P equals m over, I'm going to put the 1 plus rather than something plus 1, and then the A to the negative 1 is B, and then we've got E to the negative k mt. Okay, so that reached a really big milestone there. Damn it. Right, so that's let's just pause and think about what we've achieved here. I'm just going to make a little bit of a note. So dp dt equals kp bracket m minus p is a differential equation representing logistic growth with maximum population m. Okay. It has solution. Okay, we've just solved it in general. P equals m over 1 plus b e to the negative k mt. What are all these letters? Well, so P equals population, M equals max population b equals a constant to fit the given data. Like if you're given some initial data, then you're just going to have to work out what b is. K equals constant, which is like a growth rate, and t is time. Okay, so 3 things, 5 of them are constants. Okay, so those are the variables. So we have the population over time, and the rest of them are constants. So for our particular question, m equals 20,000, and we're going to need to work out what b and k are. Right? So we'll get on with that. So all right, so for our particular question, m equals 20,000. Okay, carrying on. So P equals 20,000 over 1 plus B e to the negative k mt. And I want to point out something. K is a constant, m's a constant. So I'm actually going to think of km as a constant. I'm not going to think of them separately. You'll see why. All right, P of 0 equals 100. That's some data that was given that initially, this is 50 years ago, 100 rabbits were placed on the island. So we have 100 equals 20,000 over 1 plus b e to the negative kmt. Now, well, I do this every time. I've written t instead of writing 0. So let me just fix that. Okay, now this is 0, which means this is 1, which means this is b. And so what we have is 1 plus b equals 20,000 over 100 or 200, and so therefore b is 199. Okay, so I'm going to write that in purple. And now we have P50 is 10,000. That's the present day. And we're going to find K now. So 10,000 equals m over 1 plus b e to the negative km 50. And remember, m is 20,000 and b is 199, but I don't have to write them out. And so 1 plus b e to the negative 50 km equals m. I suppose, all right, I'll write it this time. 20,000 over 10,000, which is 2. And so remove the 1 from both sides, we get b e to the negative 50 km equals 2. We want to find km, so e to the negative 50 km, that's 2 over b, or sorry, I need to remove 1 from that. I knew something was wrong because I've done the question before. Right. just another reminder, I could put m equals 20,000 in here, but I'm not, because I'm treating km as one constant, which is a very nice thing to do. So negative 50 km is log of that. And so km, if you just calculate it all out, km is 0.105866 dot dot dot. I'm going to write km, I'm going to write it in purple. Km approximately equals 0.1059. Okay, so putting it all together, we've got population P equals, well, 20,000 over 1 plus 199 e to the negative km, which is 0.1059 t. Okay, so we have, I don't have any letters in there other than P and T. Remember that m is 20,000, so if you wanted to find k by itself, then you divide this number, which is already small, by 20,000, and you get a decimal with a lot of zeros, and that's just annoying. Okay, and so to actually answer the question, right? I'm sorry this is so long, but I can't help it. To actually answer the question, find the number of rabbits there'll be in another 50 years and then another 75 years. So going to, that's supposed to be a straight line. Jeez. All right, I give up. Okay, so T and P. So we know that we're given values for 0 and 50, that's 100 and 10,000. And then in another 50 years, right, so this is 50 years ago, this is now, this is another 50 years, and then another, and then 75 years. So we need values of 100 and 125, and you just put it into your calculator, into this purple equation, and the values you get here are 19,900. I thought that might have been 19,990 actually, but I've written this down on my sheet of paper, and so you can do that on your calculator and see. And 125, 19,992.8781. Right? Now, of course, you'd round that, but that's not the point I want to make here. The point is going from, right, so if this is T and this is P, if you go from 100 to like 10,000 in 50 years and it's exponential, then that's really skyrocketing, isn't it? Right, so that's 50 years, 10,000, and then 100 years, well, that'd be an uncountably large number of rabbits, but with our logistic growth, it's actually from there to there, it's only doubled, you know, a little bit less than doubled. So it's approaching that 20,000 limit that we've put on. And I'd just like to comment on the equation that we've got. That for our P, right, basically if P equals M, some maximum, over 1 plus B e to the negative kmt, then what are like the minimum and maximum values here? Well, if this was 0, well, sorry, if this tends to 0 over time, and so the No, actually, I'm not commenting any further. Sorry. I'm going to GeoGebra now. Make this as quick as possible. I've set it up already. So I've set up the axes so that everything will be within view. And just typing in the equation that we found, it's got poor rounding. It says negative 0.11 instead of negative 0.1059, but hopefully internally it's got it right. So it gives us this logistic equation, and you can see that it's approaching 20,000 over the long run. If I put in the two values that we were given, so 0, 100, that's the initial, and then 50, 10,000. And just want to put in, now 50, 10,000, well the 10,000 is halfway to the 20,000. And if I put in the tangent there, you can see that it's a point of inflection. You can see that's where the concavity changes. I'm just reinforcing for you that the halfway point of the population is the inflection point, and so it proved to be in this case. Okay. The remaining questions. So at what time, let me, okay, this question. At what time does a maximum population growth rate occur? Well, it happens now at t equals 50, okay, because that's when we're halfway. So that worked out nicely for this question, but what you really need to do is solve the maximum population growth rate occurs when you are halfway to the maximum, and so you solve that for t. Question C is also solving for t. Here we are solve p of t equals, well, 90% of the maximum, in this case is 18,000. Okay, so we'll do that. So funny, these things that come along for the ride, isn't it? Off you go. Solve p of t equals 18,000, so we get, just keep the equation in view there. So 18,000 equals 20,000 over 1 plus 199 e to the negative 0.1059t. And so we get 1, well that's 0.9. If we divide through by 20,000, equals 1 over. Now, I'm going to keep writing like this because we have values for all of these and it's easier to write. So 1 plus b e to the negative kmt is 1 over 0.9, which is 1.11111. And so take 1 off both sides, b e to the negative kmt, 0. And we're trying to get t out of this, aren't we? So we can divide by b. This is all just normal stuff now, isn't it? So if we divide by b, we're dividing by 199. Then we have 0.0005583, and on it goes. And now we take logarithm. And when we divide by negative km, we've got a nice value for km here, so we can divide by negative that, and we get 70.732 ... So, you know, approximately 71 years. And that is seen here. If I literally type in y equals 18,000, then we can see the point of intersection there. Can't seem to make it register. Anyway, the point of intersection there where the logistic curve strikes 18,000, if you cast your eye down, it's just past 70. I believe that this curve is actually a little bit inaccurate because of the 0.11 in the equation. I think that's unfortunate, but whatever. Okay, so we've solved that question. Now the next one is very similar. So I'm going to try and go through it really quickly. Just has some differences. It starts from a different point. It starts by giving us a complete equation, a differential equation. So it's got the k in there. All right, so k equals 0.0024. And we've got to show that question, right? And it's a bit of a pain. I'd rather work with k and m than work with 0.0024 and 5/12, but anyway. So we'll do this, and then starting from the differential equation, do this. So we're going to be going through the same steps. So you can pause and do this yourself if you like, and then I'm going to do the solution really as quickly as I can without explaining every step. But let's just look at what we've also got. Finding the population, well, that's just substituting into there, so that's really no big deal. And what is a maximum possible population of fish for the salmon farm? Well, it's clearly 1,000 because that's the place of, that's the m. This is k, p, m minus p, right? Took the maximum. So the answer is 1,000. But let's just look at it from this point of view. And I'll just get this question out of the way first. So as t approaches infinity, I like to work we want to show that p approaches 1,000. I like to work these from the inside out. So, e to the negative 2.4t approaches 0. That's just a property of an exponential with a negative, e to the negative something. So 1 plus e, right, approaches 1, and so 1,000 over 1 plus e to the negative 2.4t, well, that approaches 1,000 over 1, which is 1,000, and what we have on the left hand side is simply p, right? So p approaches 1,000. I'd just like to remind you of this style of working because it helps you to do any question where you're looking for a long-term value. Okay, so okay, well, the dreaded days or the dreaded moment is here where I have to do all of this. So question A to start with. Oops. Right. A. Okay, I'll start with the right hand side. So it's 5/12 of keep doing that. That's 1,000. Right. Now 5/12 of 1,000 is 1250 over 3. Calculator can tell you that. What's my motivation here? The thing that we're showing has a 1 in the numerator, so I want to get a 1 in the numerator as well. But now the thing that we're showing has that in the denominator, and look, this is simply a fact. I'm just copying it out here, right? So it's like I'm fudging it in an exam, isn't it? Right? So if I'm fudging in an exam, then I need to show why, right? And all I've done is I've taken the reciprocal of 1250 over 3. Okay, so I'll just make a note as 3 over 1250 equals 0.0024. I needed to take the reciprocal to get it down into the denominator. Okay, question A is done. And Right, let's work on this. So I've got dp dt. I'm going to write kp 1000 minus p. Okay, you give me this question in an exam and I'm setting myself up like this because I do not want to write 0.0024 every line. I will live with writing 1000. Okay, dt dp. So I'm going to use this now. And I can integrate with respect to p. And okay, there we go. Okay, I'm going to deal with this and this at once. I'm going to do 12/5 t minus c equals ln. Now, note that c has changed value in the last line because I should have multiplied it by 12/5, but I'm not going to. It's just a constant. You know the drill. P over 1000 minus P equals, now 12/5 is 2.4, so it's e to the 2.4 t times e to the negative c. Now we've got e to the 2.4 t, whereas here we get e to the negative 2.4 t. Why the difference? Well, this is in a denominator and we're not there yet. Okay, we're not up to a denominator yet. So that will come when we divide by e to the 2.4t later on. And now, the textbook says we can get rid of the absolute value signs because because population is positive. Now, population is a positive quantity, but say P equals 2000. That's positive. Well, then P on 1000 minus P is 1000 over negative 1000, which is negative. So I don't want to rush to the conclusion that this is positive, or sorry, that this is positive, and therefore we can remove the absolute value signs. So I'm not about to do that. Okay, so I've dealt with the absolute values by allowing that A can be positive or negative. If we considered a constant solution, then it could be 0, but I'm not going there. And now we have to get P. Oh, I've got P in two places. We've got to get P by itself. All right, speeding up again. bottom by AT. Okay, this is where the negative comes in. And let B equal. Okay, so we have we have something awesome. And now started a salmon farm with 250 fish. So we can find the value of B pretty easily. So, so T equals 0, P equals 250. So all right, there we go. Done. I did all this before. Done everything now. Okay. So that's the logistic equation. Now, question 8. This will be quite quick. Write down the general solution of ds dk equals ks p minus s. So we've got some different nomenclature here. So S is our population. Why is it that? Because we're looking at an area later on, so square millimeters. So think of surface area of a biological culture. P is just a constant. So don't think of P as population. I know it's confusing, but we have to be able to deal with confusion. So P is the maximum surface area. So the general solution of this is S equals P is the constant, the maximum, over 1 plus B E to the negative K P T. Okay, just think of what we would normally have. Right, so that appears in those places. It's the same thing. Okay, hence answer. Assume that the growth of a certain biological culture measured in square millimeters is modelled by this differential equation. So K equals 0.0020. Why that's 0? Because it's 4 significant figures. 800 minus S, so the maximum, so that's our value P, is 800, where S denotes the size of the culture measured in square millimeters at time t. When first observed, the culture occupied an area of 100 square millimeters. So A, determine the size of the culture at time t. That's really saying find S in terms of t, or just find S of t, right? So solve the differential equation. So S equals P over 1 plus B e to the negative kpt. Let's put our details in. So we've got P is 800 over, so B we have to find, e to the negative kp, right? So we've got P equals 800, K equals 0.0020, so therefore Kp equals, I've got this written somewhere, calculator. Calculator. 1.6. Negative, negative 1.6t. Right, so we're nearly there. We just need this, and we get that from s of 0 equals 100. We get that from information given. I just want to quickly point out here that we know that when we put in 0, this all goes to 1. So basically, 800 over 1 plus b is 100. So 1 plus b is 8, so therefore b is 7. Okay? Anyway, so 100 Okay, so we've found that. B, at what time does a culture grow most rapidly? Correct to 4 significant figures. Okay, so most rapid growth occurs when P equals, not P, when S equals 800 on 2, it's 400. Right, so we'll solve for that. So we'll solve S of T equals 400. Right, I'm back into fast mode. Okay, can I just point out how obvious this is, that we're solving for s equals 800 over 2, so this means that the denominator needs to be 2, which I just took a few steps to find out. All right, if I was doing it myself, I would use that kind of, if you like, advanced common sense, but I'm not doing it for myself, I'm doing it for you. So, all right, subtract. All right, and so on, and we get t equals 1.216 ... time units. We weren't told in the question what the units of time were, I don't think. So they were done. It's interesting, when I first recorded this video, but then found afterwards that the microphone was off, so I've had to do it all again. I actually did it like this. So here we are. Right, so the max growth occurs when S of t equals p on 2, right? Remember, p is our maximum in this case. So i.e. 1 plus b e to the negative kpt equals 2. Right, so I kept everything in terms of the constant letters instead of their particular values, and then found that t equals lnb over kp. Right, so this is actually something that's generally true for any logistic situation. The time at which the maximum growth occurs is the log of the b constant, which you have to find if you're getting anywhere, divided by k times the maximum population. All right, so that's true for any, I'm not saying remember it, I'm just saying it's kind of nicer to work with this than it is to work with this. Okay? All right, that is the end of video 6G.